parallel operation. Power flow equation. I will introduce the contents we are going to discuss power flow equation and synchronization, and coming to the of change mechanical power alternate determination of transient steady state reactances. I am going to discuss the various topics. The third chapter of the parallel operation. I will start with the first I will take the power flow equation. So here I am taking a star connection for alternate operating on infinite bus. Here I am taking a star connected cylindrical rotor alternator operating at bus. So actually it consists of the parameters like V is equal to bus bar voltage phase and E phase, and IA is armature alternator, and next ZS, that is the sync per phase. So that is equal to RA plus JX. The known formula for all of us. Impedance per phase is equal to RA plus JX. And cos phi, that is the lagging power factor of the alternator, and theta is the internal angle, that is equal to tan inverse of x RA. These are the various parameters we are going to use the power flow equation for alternators. Okay. The diagram I am taking. So on the left side we have the circuit arrangement for this power flow equations of a cylindrical rotor. Okay, so here it consists of the generator or alternator. It consists of the E voltage, and it also consists of the current, and in series with the synchronous impedance, and it consists of the voltage. There is a terminal voltage. And next after that we have the phasor diagram of this concept. So here I am taking the voltage as a phasor reference line. So that is indicated as a horizontal line V. Okay, and next I am going to draw the IA value. So actually this IA value is lagging by angle phi. Okay, and after that I am going to draw the EMF line. That is EMF line is in leading with the voltage line, that is in the uppercase of this one. Voltage line uppercase, we have the line straight line, that is the E, and the angle difference between V and E is delta, and we have voltage drop, that is IAZS, that is the synchronous impedance drop, that is IAZS. So that line is parallel with the voltage line, voltage phasor line. Okay, and here it is connected to the armature current also, because of it is the voltage drop. It consists of two parameters. One is armature current and another one is synchronous impedance. So that's why I am indicated with the dotted lines, and the angle between these two is theta. That is the internal angle. Okay, this is the phasor diagram and circuit arrangement for this derivation of the power flow equation in a cylindrical rotor alternator type. Okay, next. So I already said that the figure shows the first one, that is the figure A, shows the equivalent circuit of one phase of the alternator. Okay, that is the equivalent circuit of one phase of the alternator. So actually here it consists of three phase, but here every parameter I will take into the single phase only. That's why I am showing that the figure shows the equivalent circuit for one phase of the alternator, that is on the previous diagram. First diagram on the left side we have the diagram, that is the equivalent circuit of one phase of the alternator. Next figure B shows the phasor diagram, that is the right side of that diagram. We have two diagrams, one on the left side and one on the right side. Left side of the diagram consists of the equivalent circuit of an single phase alternator, and right side of the diagram shows the phasor diagram of that arrangement. And next, note that drawing the phasor diagram, so V has been taken as the reference phasor. So I already said in the previous slide only. So in the phasor diagram, I am taking the voltage as the reference line. Okay, next, by using that phasor diagram and equivalent circuit, we are going to derive an expression for the power delivered by the alternator, referring to the figure A, that is the equivalent circuit of single phase alternator, one phase alternator. So for that circuit, I am applying the KVL to the circuit. So finally we have the expression that is E at an angle of delta is equal to V at an angle of 0 plus IA ZS at an angle of theta. So from the diagram I am applying the KVL to the circuit. We have the expression that is E at an angle of delta, that is equal to V at an angle of 0 plus IA ZS at an angle of theta. So from this one I will rewrite that equation into IA is equal to E at an angle of delta minus V at an angle of 0 divided by ZS at an angle of theta. So from this one I am also write E by ZS of E by ZS at an angle of delta minus theta minus V by ZS at an angle of minus theta. Okay, this is the expression for the armature current in this arrangement. Okay, IA is equal to E by ZS at an angle of delta minus theta minus V by ZS at an angle of minus theta. This is the expression for the armature current. Next, so coming to the power output per phase. So actually, from the previous expression, I am writing power output per phase P is equal to V into real part of IA. That is from the armature current equation. Okay, so V into real part of IA, coming to that equation. So V into real part of that equation is E into cos of delta minus theta minus V cos of minus theta by ZS. That is the real part of armature current from the previous equation. And we will multiply with the V. V consists of EV cos of delta minus theta minus V square cos of minus theta whole divided by ZS. So from this one we are writing real power output is equal to EV cos of delta minus theta minus V square cos theta by ZS. Okay, we will rewrite the real power output is P is equal to EV cos of delta minus theta minus V square cos of theta by ZS. Treat this one as equation number 1. Okay, this is the real power output per phase. And next, coming to the maximum power output. So previously we derived the power output per phase, and now I am going to discuss maximum power output for that case. So for given E and V and frequency, that means EMF, voltage and frequency, the conditions for maximum power output can be obtained by differentiating that equation number 1 with respect to delta and equating the result to 0. That's why I am taking this one in the mathematical form, that is dP by d delta is equal to 0. Why I am taking this one? To determine the maximum power output from the equation for the equation number 1. That's why I am taking dP by d delta is equal to 0. So here I am writing d by d delta of in the previous equation, the P equal to, what is the equation? That is EV cos of delta minus theta minus V square cos of theta by ZS, that is equal to 0. And differentiate this equation with respect to delta, we will have the equation that is EV by ZS into sine of delta minus theta. So that is equal to 0. From this one, delta minus theta is equal to 0 and delta is equal to theta. So treat this as equation number 2, and to get the maximum power, substitute the above condition, that is equation number 2 in equation number 1. So what is the equation number 1? EV cos of delta minus theta minus V square cos of theta by ZS. So in that equation we have to substitute in the place of delta, we will replace with the theta, and after that we have the P maximum is equal to EV cos of, in the delta place I am substituting theta, that's why we have theta minus theta, that is 0. So that is EV cos of 0 minus V square cos of theta. So in theta plus theta only. So V square cos of theta by ZS. And from this one we are writing P maximum is equal to cos 0 means 1. That's why we have EV minus V square cos theta by ZS. Okay, by ZS. Next. So here I am taking the approximate expression we have seen above, that equation number 1, that is P is equal to EV cos of delta minus theta minus V square cos of theta by ZS. So in this case I am taking, if the armature resistance is more or less than ZS, then theta is equal to 90 and ZS is equal to XS. This is the condition I am taking. Okay. So if armature resistance Ra is more or less than Zs, then theta is equal to 90 degrees and Zs is equal to Xs. So these two conditions we have to substitute in the first equation. So if you substitute that into this equation, we will get P is equal to EV by Xs into sine delta. So to get now power per phase is given by P is equal to EV by X into sine delta Y, because here cos in the theta plus I am substituting 90, so that's why we have the cos 90 value is 0. Okay, so cos of delta minus 90 we have, so cos of delta minus 90 is equal to sine delta from the trigonometric functions. Cos of delta minus 90 is equal to sine delta. So from that one we have P, if we substitute that cos 90 is equal to 0 and cos delta minus 90 is equal to sine delta, we have P is equal to EV cos of delta minus 90 minus v square into cos 0 by Zs. So finally we have the P is equal to EV by Xs into sine delta. So to get the maximum power, substitute delta is equal to 90 degrees to the previous equation. We have P maximum is equal to EV by X into sine 90. So from the trigonometric functions, sine 90 is equal to 1. So substitute here. So finally we have the maximum power P maximum is equal to EV by XS. This is the expression for the maximum power output. Okay. So, and coming to the power angle characteristics for a power flow equation of a cylindrical rotor type alternator. So, the power output of an alternator is given by power per phase is equal to P is equal to EV by Xs into sine delta. EV by Xs into sine delta. So, from this one I am drawing a power angle curve or power angle characteristics. So, here the characteristic diagram is drawn between power angle versus maximum power angle versus power. So that is delta versus P. So here I am drawing a curve. So it is a half sine, it is look like a half sine wave. So here whenever the angle increases, the power also increases up to certain point, up to it reaches the maximum power. It comes like this, and after reaching the maximum power, it will slightly decreases. Okay, and it touches to power angle at some angle. Okay, so at 90 degrees we have the maximum power per phase. Okay, so that is P maximum is equal to 3 into EV by XS. So actually this is for the 3-phase, but for a single phase we have P is equal to EV by XS. EV by XS. So this is the power angle curve for the cylindrical type alternator. And note that the power output varies sinusoidally with power angle delta. So I already said that here we have the half sinusoidal, not full sinusoidal, but in this one also up to saturation point we are increasing. That's why whenever it reaches the maximum power, and after that it will decrease slightly. So the decreasing order I will show in the dotted lines, and the thick line is shown that it is a maximum power condition at 90 at delta is equal to 90 degrees. So note that power output varies sinusoidally with power angle delta. So the figure shows the power angle characteristics of the alternator, and the alternator delivers maximum power when delta is equal to 90 degrees from this diagram. So if delta becomes greater than 90, the machine will lose synchronism. That's why the curve is in a decreasing manner. Okay. So next, coming to the next one, that is power developed in salient pole synchronous generators. Salient pole synchronous generators. So in this case, I am neglecting the armature resistance Ra, then power developed by an alternator is equal to the power output. So actually here I am taking the two conditions. One is here I am neglecting the armature resistance. That means copper losses we are neglecting. Then second one is here the power developed by an alternator is equal to the power output, that is PD is equal to P out. So I will show the phasor diagram of the salient pole synchronous generator. It will give the clear idea about this one. So this is the phasor diagram for the salient pole alternator. So here we have so many parameters. Okay, so voltage, armature current and quadrature current and direct axis current. And next we have the drops, that is IQ, XQ and ID XD, and the E naught line and the angles delta and phi. So here the voltage. So here I have firstly drawn the IA line. So this IA line and V line are in the leading condition, that is IA leads the voltage at an angle phi, and after that we will draw the line, that is IQ and ID. So this IQ and ID is in phase quadrature with these two terms at an angle delta. So that's why I am taking IQ and ID in different lines. So ID is in the parallel with the IA and it is in series with the IQ. And next for that line, I am taking the EMF line. So that is in the that line. And next I am taking the two drops, that is IQXQ drop and IDXD drop. So for that one I am taking the drops, I am taking from the V line. So from the V I am drawing a straight line. So it consists of IDXD drop, and after that we are drawing a one horizontal line. It touches the E naught line, that is IQXQ. So this is the phasor diagram for the salient pole machine. Okay. So next, so the per phase power output of the alternator is P out is equal to, that is equal to PD. That means I already said that the developed power is equal to output power of the alternator. That's why I am taking P out is equal to PD. That is equal to V into IA cos phi. V into IA cos phi. So now IA cos phi is equal to, so this one is divided into two terms. One is IQ and ID. So from this one I am writing IA cos phi is equal to IQ cos delta plus ID sin delta. From the phasor diagram I am writing this one. And also E naught is equal to V cos delta plus ID XD. That is also from the phasor diagram. So E naught is equal to V cos delta plus ID XD. So from this one I am writing ID is equal to E naught minus V cos delta by XD. And V sin delta is equal to IQ XQ. This is also from the phasor diagram. V sin delta is equal to IQ XQ. So from this one I am writing IQ is equal to V into sin delta into XQ. So IQ is equal to V sin delta into XQ. Next, power developed, that is P out is equal to PD is equal to V into IA cos phi. Okay. So here I am writing PD is equal to V of IA means IA cos phi means you have IQ cos delta plus ID sin delta. Substitute here that expression IQ cos delta plus ID sin delta. Next, from this one we have V into V sin delta into XQ into cos delta plus E naught minus V into cos delta into XD into sin delta. So from this one I am writing V square sin delta into cos delta into XQ plus E naught minus V minus V sin delta by XD minus V square sin delta cos delta into XD. Okay. So from the above equation I am writing V square sin delta into cos delta into XD plus, so E naught minus V into sin delta by XD minus V square sin delta cos delta into XD. So here I am writing E naught minus V sin delta by XD plus V square sin delta cos delta into, so this will I am writing XD minus XQ by XD into XQ. XD minus XQ by XD into XQ. So from this one I am writing E naught V sin delta into XD plus I square V square sin 2 delta into XD minus XQ by XD XQ. So finally we have this expression, that is E naught minus V into sin delta into XD plus I square V square into sin 2 delta into XD minus XQ by XD XQ. So from this one I am telling the total power developed would be 3 times the above power. The total power developed would be 3 times the above power. Next, the following points may be noted, that is, if there is no saliency, at that time the reactance XD is equal to XQ. So from this one I am writing P is equal to EV by XD into sin delta. EV by XD into sine delta. So this is the power developed by cylindrical rotor machine. This is the power developed by the cylindrical rotor machine. And the second term in the equation number 1, so that is introduces the effect of salient poles, and it represents the reluctance power, that is power due to saliency. That is power due to saliency. Next, coming to the power angle characteristics of the salient pole machine. So this is the diagram shows the power characteristics of the salient pole machine. So here the curve is drawn between angle delta and power. So here we have three curves. The thick line gives the total power curve, and the two dotted curves is there. So one curve it is shown like a half sine wave. So it is for the excitation power. This excitation power is directly proportional to sine delta. And one more curve is there. So this curve is a purely sinusoidal. So this curve is known as reluctance power, and it is also directly proportional to sine 2 delta. Okay, these are the three curves we are taking for the salient pole machine. So total power, excitation power, and reluctance power. Okay. So next, so the figure shows the power angle characteristics of salient pole machine. There is a previous diagram. So from that one, it is clear that the reluctance power varies with at twice the rate of excitation power. The reluctance power varies with the twice the rate of the excitation power, and the peak power is seen to be displaced towards delta is equal to 0. The amount of displacement depends on the excitation. Okay. Next, in the figure, the excitation is such that the excitation term has a peak value about 2.5 times that of the reluctance term. 2.5 times that of the reluctance term. So, under steady state conditions, the reluctance term is positive because xd is greater than xq. This is the under steady state condition. Okay, the reluctance term become xd is greater than xq. That is positive. Next, so up to now we discussed about the power flow equations in cylindrical rotor type and salient pole rotor type. And next I'm going to discuss the synchronizing power. That is P suffix Sy. That is represented as P suffix Sy. Firstly, I will give the definition of the synchronizing power, and after that I will give detailed explanation about this one. So firstly, the synchronizing power is defined as the difference between input power to alternator at power angle delta. Okay, synchronizing power is defined as the difference between input power to alternator at power angle delta and input power to alternator at power angle delta plus delta dash. Delta plus delta dash. This is the synchronizing power, and it is denoted with the letter P suffix Sy. And here I am considering an alternator connected to the infinite bus bar. Okay, so here I am taking the diagram. Okay, so an alternator connected to the infinite bus bar. So in that one we have V, that is the bus bar voltage, and EB, the EMF induced in the alternator. Okay, next the excitation of the alternator is adjusted in such a way that E and V are in equal magnitude. Okay, the excitation of the alternator is adjusted in such a way that E and V are equal in magnitude. So here I am taking two circuits, one is external and one is local. So in the local circuit, the two voltages E and V are in phase opposition, while in the external circuit they are in the same phase. I will show the diagram, two diagrams. So this is, so in the external circuit, the E and V are in the phase opposition, are in the same phase, and in the local circuit these two are in the opposite directions. Okay, and next, so consider the alternator to be at no load. So here I am considering the alternator to be at no load. So it may be some means power input to the machine is decreased and its induced EMF E will be lag behind V by say an angle 2 delta. So in sometimes the power input to the machine is decreased and its induced EMF E is the lag behind V by an angle 2 delta. So due to this difference, E and V will not remain in exact phase opposition but will give rise to resultant EMF, that is ER. Okay, so this ER will act in the local circuit and a synchronizing current will start flowing in the local circuit. Okay, the synchronizing current will start flowing in the local circuit. So the synchronizing current is given by I suffix Sy is equal to Er by Zs, that is the resultant EMF divided by synchronous impedance, that is the synchronizing current. So synchronizing current is defined as the ratio between resultant EMF and synchronous impedance. So here the synchronizing current is lagging behind ER by an angle theta is given by theta is equal to tan inverse of XS by R. That is, the XS is synchronous reactance. Here the R is very small and it can be neglected. That is theta is approximately equal to 90 degrees. Theta is approximately equal to 90 degrees. So the angle 2 delta is very small and theta is approximately equal to 90 degrees. So the synchronizing current ISY is almost in phase with V and in phase opposition with E. Okay, ISY, I suffix SY, that is the synchronizing current, is almost in phase with V and in phase opposition with E. So infinite bus bar will deliver some power to the alternator. So at that time the infinite bus bar will deliver some power to the alternator. So as the current in the local circuit is always opposing to induced EMF E, the alternator will act as synchronous motor. Okay, as the current in the local circuit is always opposing to induced EMF E, then the alternator will act as a synchronous motor. Next, the synchronizing torque will be developed, which will try to accelerate the machine. So here some synchronizing torque will be developed. Why? Because it will try to accelerate the machine. So thus the angle 2 delta will go on decreasing and resultant EMF ER also goes on decreasing. So the angle 2 delta is decreasing and the resultant EMF ER also decreasing. So finally the two EMFs, that is E and V, will again be in phase opposition and machine will now act as an alternator in synchronism with the bus bar. Okay, like that it will operate. And this is the phasor diagram I am taking. So here I am taking a 4 quadrants, okay, but the operation mainly in the 3 quadrants. So here I am taking the V line and ER line and ISY line and E line. So here the angle between V and resultant EMF ER is theta. And next I am drawing a synchronizing current line. It is in a series, it is in a parallel with the voltage line, that is ISY, and I am drawing a EMF line E. It is in exact phase opposition and it lags the voltage by 2 delta. Here the phase difference is 2 delta and the angle between resultant EMF and synchronizing current is theta. The angle between ISY and ER is the theta and the angle between V and ER is also a theta, that is theta by 2. Okay, like that we are drawing this phasor diagram, and thus the power which automatically comes into play and accelerates the machine which was retarding and decelerates the machine which tries to accelerate is called synchronizing power. Okay, the power which automatically comes into play and accelerates the machine which was retarding and decelerates the machine which tried to accelerate is called synchronizing power. Okay, the power will keep the machine in step with the infinite bus bar. The power will keep the machine in step with the infinite bus bar. Next, coming to the expression for the synchronizing power. So here I am considering an alternator which is operating at a power angle delta, that is E leads V by an angle delta. So here the V leads the E at an angle delta, and here we have one more curve, that is E dash. So here the phase difference between E and E dash is delta dash. Okay, and also we have one more line, that is the drop line. It is in connection with the E dash and E. Okay, next, let power input of this alternator can be increased suddenly so that it will now operate at a new phasor power angle, that is delta plus delta dash. So actually it is the angle is delta, but whenever the alternator power input is increasing suddenly, so it will now operate on a new power angle, that is delta plus delta dash. So the synchronizing EMF, that is E suffix sy, will come into play, okay, and sends a circulating current given by ISY, that is synchronizing current, is equal to E suffix sy by Zs, that is the synchronizing EMF by synchronous impedance, and this current produces synchronizing power. Okay, this current produces synchronizing power. That means now we will derive the expression for the synchronizing power per phase. So before increasing the input of alternator, the power input Pi1 is given by, so before increasing the input of alternator, the power input Pi1 is given by Pi1 is equal to E by Zs of E cos theta minus V cos of theta plus delta. Okay, that is the power input 1, that is Pi1, E by Zs of E cos theta minus V cos of theta plus delta. Next, so when power angle delta has been changed to delta plus delta dash, that means plus or minus delta dash, that means plus sign indicates the acceleration and the negative sign indicates the deceleration. Okay, at that time the power input Pi2 is given by, so Pi2 is equal to E by Zs of E cos theta minus V cos of theta plus delta plus or minus delta dash. So the difference between these two powers is nothing but synchronizing power Ps. So that is Psy is equal to Pi2 minus Pi1. So that is power input 2 minus power input 1. And here I am taking the 2, that is Pi2 means, you know, E by Zs of E cos theta minus V cos of theta plus delta plus or minus delta dash minus of E by Zs, that is Pi1, E by Zs of E cos theta minus V cos of theta plus delta. Okay, next we will simplify this one. We have E by Zs of V cos theta plus delta minus V cos of theta plus delta dash, and this case is for the considering the positive sign for delta dash. Okay, here we have two conditions. One is positive and another is negative. Positive for the accelerating and negative for the decelerating. Firstly, I will consider the positive sign for delta dash, that is the accelerating. So we have EV by Zs, EV by Zs, that is I am taking the V common, that is EV by Zs of cos of theta plus delta minus cos of theta plus delta into cos delta dash minus sin of theta plus delta into sin delta dash. So from this one I am writing EV by Zs of sin of theta plus delta into sin delta dash plus cos of theta plus delta into 1 minus cos delta dash, and from this one I am writing EV by Zs into sin of theta plus delta into sin delta dash plus cos of theta plus delta into 2 sin square delta dash by 2. So we will write 1 minus cos delta into 2 sin square delta dash by 2. Okay. Next, so if delta dash is small, then delta dash by 2 is very small. Okay, therefore sin square of delta dash by 2 can be neglected as it is tending towards 0. That's why I am writing synchronizing power, that is equal to V by Zs into sin of theta plus delta into sin delta dash. And for large synchronous machines, theta is equal to 90 and Zs is equal to Xs as Ra is neglected. That's why we have Ps is approximately equal to V into E by Xs into cos delta, that is sin theta, that is 90. So sin 90 plus delta, that is nothing but cos delta from the trigonometric function into sin delta dash. So here in the Zs plus I am taking Xs, and in the theta plus I am substituting 90 degrees. After that we have the final expression for the synchronizing power, that is equal to V into E by Xs into cos delta into sin delta dash. And next, so for synchronous generator which is synchronized with bus bar V, so that is at this condition V is equal to E and delta is equal to 0 and delta dash is very small. After that we have in the sin delta dash plus we have to substitute the delta dash, and in the cos delta plus we have to substitute 1, and for large synchronous machines theta is equal to 90 and Zs is equal to Xs and Ra is neglected. So that's why we have the Psy is equal to, in the E plus we have to substitute V, that's why we have the V squared by, in the Ra plus we have to substitute, in the Zs plus we have to substitute Xs, that is V squared by Xs into delta dash. Okay, so in the sin delta dash plus we have to substitute delta dash, that's why we have V squared by Xs into delta dash, so that is equal to E squared by Xs into delta dash, and that is equal to E of E by Xs into delta dash, so that is equal to E into IS into delta dash. Okay, this is the synchronizing power expression. And next, the above expression is for the phase power. Okay, therefore, for machine having m phases, the synchronizing power is given by P suffix sy is equal to m into E into I into delta dash. So here m is the number of phases we are taking. So previously we have the single phase, that is PSY is equal to E into ISY into delta dash, E into I into delta dash. But for a M phase, we have PSY is equal to M into E into I into delta dash. Okay. And the same expression is not valid for salient pole machine. So the expression for the salient pole machine can be obtained as follows. So up to now we discussed about the expression for the synchronizing power. But here I am taking the expression of synchronizing power in salient pole machines. So previous expression is not valid for the salient pole machine. That's why I am taking the another expression. So for that one I am taking the two phase diagrams A and B. Okay. So in the first phase diagram, I am taking the voltage is in leading with the E at an angle of delta, and it is also lagging with the I, that is with an angle phi, and it consists of the IA is in phase with voltage, that is IA and V all are in, both are in the same phase. Okay, and the IQ line touches the IA and IA. That means the I is equal to IA plus. Sorry, here I am taking the IQ and ID. So it touches the ID is in between voltage and current, and the IQ line is between E and V line, and it touches, both line touches IA and V line. Okay, IQ and ID. And next we are drawing a parallel line to the I, that is IR line. Okay, at an angle delta. Okay, so like that we are drawing this phase diagram. On the left, on the right side we have one more. So it consists of same lines. So here also the voltage leading with the E at an angle of delta and I with an angle phi, and here we have the voltage drops, that is IQ XXQ and IDA as XSD. So that is the quadrature axis, and for the direct axis we are taking this. Okay, these are the voltage drops we are taking. So from the figure, that is from the diagram 1, it can be observed that E is equal to V cos delta plus ID into XSD. So from the figure 1, that is on the left side of the diagram, that is E is equal to V cos delta plus ID into XSD. So from this one I am writing ID is equal to, that is the direct axis current, E minus V cos delta by XSD. Okay, next V sin delta is equal to XSQ, that is also from the figure A, that is V sin delta is equal to XSQ. So that's why IQ is equal to V sin delta by XSQ. Next, from the diagram B, that is from the another phasor diagram, it can be observed that IA is equal to, that is armature current is equal to I cos phi. So that is equal to the I current is divided into two components, that is IQ and ID. So that's why I am writing this equation as IQ cos delta plus ID sin delta, and the resultant current IR is equal to I sin phi. So here also it consists of two terms, that is ID and IQ. So here I am writing ID cos delta minus IQ sin delta. These are the armature current and resultant current of the second phasor diagram. And so coming to the power output equation, so you know already the equation, that is V into I into cos phi. So that is equal to V into I cos phi, means previously we derived that one, that is IQ cos delta plus ID sin delta substituted here. After that we have the V into, so V of V sin delta by XSQ into cos delta plus E minus cos delta by XSD into sin delta, that is IQ and ID values, these are IQ is V sin delta by XSQ and ID is E minus cos delta by XSD, substituted here, and we have V into E sin delta by XSD plus V square sin delta into cos delta of 1 by XSQ minus 1 by XSD. Okay, this is the power output. And next we have few more. So that is equal to V into E into sin delta by XSD plus V square into, so sin delta cos delta. So that's why I'm writing this one as 2 into sin delta cos delta by 2 into XSD minus XSQ by XSD into XSQ, and we will write this equation as VE sin delta by XSD plus V square into XSD minus XSQ by 2 XSD XSQ into sin 2 delta. Okay, like this we will write, and thus the total power consists of a fundamental component. So the total power consists of the fundamental component and a second harmonic component, which is present because the armature reaction flux has a tendency to pass through the field structure along its minimum reluctance path, that is along field pole axis and direct axis. That's why I am taking XQ and IQ and X and XD and XQ like that. And since 2 delta exists because of difference in reluctance along P and Q axis and is called reluctance power, and the term is called reluctance torque. The first term is identical with that obtained for the cylindrical machine, and component of power is known as electromagnetic power, and now dP by d delta gives the synchronizing power. Okay, and this is the final expression for the synchronizing power, that is P suffix Sy is equal to V into E into cos delta by XSD plus V square into cos 2 delta into XSD minus XSQ by 2 into XSD into XSQ. This is the expression for the synchronizing power. Okay. Thank you. Thank you for watching this video. And in the next class, I'm going to discuss synchronizing torque and parallel operation of alternators and synchronization of alternators. Okay. Thank you.